Okay, so last time, in the last part of the lecture, we were discussing covariant derivatives. Okay, and we didn't actually finish discussing them. So this is what we are going to continue this lecture. So we said that when you just take the usual derivative for any tensor higher than rank 0, like, for example, a vector. So I'll get two parts. The first part is going to transform as a tensor, a second rank tensor, and another part which is going to have a very weird looking transformation, which is this part. And this spoils the transformation property of this very simple derivative. Okay? So this is why we are not going to use this operator as a derivative. We are going to modify it a little bit. Okay, so our operator is going to look like, so for example, let's apply this new operator on a contravariant vector like this one. Okay? So in this case, I'm going to do the usual derivative first. Then I'm going to have an extra term which depends on some object, call it connection, gamma. And this object looks as follows. So it depends on the first derivatives of the metric. So if I'm going to define it, I should define it this way. So this is the definition of this new object that I have. This object has a property that it is symmetric in its down indices. It's called connection. Okay? And it is there to keep the derivative transforms as a tensor. That's to say now, okay, see this object does not transform as a tensor. Now this object, okay, transforms as a tensor. If you do the coordinate transformation, you will find that this guy here transform as partial x by partial x as usual, partial x prime by partial x, and the old guy is going to be here. Okay? It transforms perfectly as a second rank tensor. Notice that when we take a derivative, we make the rank of the tensor higher, right? With 1 degree. So if it's a vector, it should be a tensor second rank. If it's a tensor second rank, it should be a tensor third rank, and so on. This connection, its definition, actually, you can get it in various different ways. Of course, we are not going to discuss that because the derivation to get it is actually a bit long, and of course will take like half a lecture with us. But the main idea is the following. Why I need this extra guy here? Let's try to understand this in a geometric way. Remember we said before that I can deal with geometric objects like vector tensors in pure geometric way, okay? But here, when we discuss its transformation, for example, like if I have a contravariant vector like this one, and I'm actually trying to see its transformation properties, what I'm really doing is I'm actually expressing this transformation in terms of its components. So A mu here and A prime alpha, these are the components of the vector in certain bases, okay? But it's always good to deal with the geometric object as a whole. But you would ask me, what do you mean by that? Remember when we used to write a vector like this, ax, ex, ay, ey, and so on, okay? So this is the full geometric way of writing an object, okay? Now you can express it in these bases, I, j, k. What we mean by bases? I mean, for people, I have here x, y, z, okay? And with each of these, I have I, j, k, unit vectors, right? But if I change the axes like this one, I could have x prime, z prime, y prime, and different also, let me call them I prime, j prime, and so on, k prime. So these are different bases, different unit vectors through which I can express my vector. I can do the same thing also with tensors or vectors in 4 dimensions. So let's try to do that. So I have a vector in 4 dimensions which I can write as v mu, e mu. Okay? Express it in terms of some basis vectors. Okay? Now let's try to change this and try to understand the derivative of such a quantity. So when we do that, if I take the variation of this whole object, okay, I'll have a variation of the two factors here. The first one, which is v mu, e mu, and the second one is v mu, the change of e mu. Okay? It's very important to realize here, when I change a vector, a geometric quantity, I'm not only changing its components, I'm also changing its basis, the description through which I'm expressing this object. And this guy here is the source of the connection that I have discussed here, this extra term. Okay? We will see that because, first of all, when you express this guy, delta hat mu, I can write it, of course, as e hat mu partial x alpha delta x alpha. Okay? Using the usual variation with respect to certain number of variables. You can see the change of this vector is proportional to delta x, okay? But also, this vector this is a change of a vector. And of course, I can always write it in terms of the basis itself, okay? Which means that I can write some coefficients. I'm going to call them gamma. Okay. And I can have, or let me do it differently here. Let me do just the variation, like this one. So I'm going to actually express partial E mu by partial x mu, and I'm going to expand them in terms of the usual basis. Okay? So now if I multiply with delta x mu to get this guy, okay, I would multiply here also with delta x mu. Okay? In other words, this is delta E mu. Okay? So in other words, this change of the basis vector, I can write it in terms of the basis, because again, the change of a vector is a vector. Since it is a vector, any vector, I can write it in terms of these bases, right? Is this clear? Or a bit confusing? The change of a vector is a vector. Since it is a vector, I can write it in terms of any basis that I like. I would choose the same basis and write it down in terms of it, and I get the coefficient of this linear combination that I'm writing. These are the gammas. Okay? Now I put this back here, okay? And what I get is the following. Delta V by delta x beta. Now I just divide everything by delta x beta and see what I'm getting here. I get partial V by partial x beta alpha. Now I've changed this dummy indices. This is a summation over mean. Does it matter if it's mu or alpha or beta? No, I can change it whatever. Okay? And since here I have a summation alpha, let's have the same notation just to be able to collect terms. So I can do that here. And what I'm going to get is this expression for the variation of the geometric object as a whole with respect to the coordinate system, and of course in the basis that I'm working with, in other words, which I choose. Of course you can change the basis whatever you like. And what is this quantity? This quantity is the derivative beta of V alpha. This is the covariant derivative. So you can see this extra term is coming from the fact that when you do change this geometric object, you're not only changing the component, you're also changing your description, the basis. Okay? And you can actually see this if you use spherical polar coordinates. Okay? When you use spherical polar coordinates and try to change your vector a little bit, you'll find also that you are changing the basis a little bit. But you won't see this in Cartesian coordinates, right? Because Cartesian coordinates does not change. For example, let's suppose that I have here x, y, z. This is a Cartesian coordinate, and you are changing your vector from this to that. Okay? And now you are decomposing your vector, the old one and the new one. Does I, j, and k change when you change the vector? No, it is the same direction. Okay? But what happened when you do the same thing with spherical polar coordinates? Let's see. In spherical polar coordinates, let's say that this is our r and this is our theta. And of course, this is going to be our phi. Let's suppose that x is here, y, and this is z. Okay? So see the directions of r hat, theta hat, and phi hat. Okay? So for example, theta hat, okay, for the normal direction of increasing the theta, this is E theta, right? Now, if you change theta a little bit here, you will find it is changed, right? So when you change the point, when you change the vector in spherical polar coordinate, actually in any coordinate system, it does make a change for the basis. Okay? But not the Cartesian. Okay? So this is why this fact is even true in flat space, but with different coordinate system than Cartesian. Okay? This way of understanding how the geometric object, which is a vector, changes is important even for general coordinates. Okay? Any question about covariant derivatives so far? Any comment? Any question? Okay, so let's move to our today's topic, which is I'm going to just express Maxwell's equations in relativistic form, which is very important for us to understand Einstein field equations. So we'll go back a bit for special relativity again before we discuss certain topics in general relativity. Okay.
Doctor,
Yes.
does it mean that the connection in the flat space is equal to zero, or doesn't, or not? Or
That's a very good question. So let's suppose that I have a flat space like ds squared, something like dx squared plus dy squared plus dz squared. And I can express it in different coordinates. This is a Cartesian coordinate. I can express it in another coordinate system, which is the spherical polar coordinate, the one we were discussing. Okay? It is the same space, but in different forms, in different coordinates. If you calculate gamma out of this one, you will find all the components are zero, the Cartesian. But the other one is not. If you calculate gamma from here, you will find some components are not zero. Does this mean that we are, when we use spherical polar coordinates, we are in curved space? No. So what is the definition of curved space? It is not through connection, definitely. It is through what we are going to discuss at the end of this lecture, Riemann tensor. Okay? Which we can express in terms of a derivative of this connection. If this is vanishing everywhere, or if this is vanishing in general, this is a clear sign of trivial space, flat space. Okay? If it's not vanishing, this is not a trivial space, so it's curved space. Okay? So for example, when you do the connection here, this is not zero, but when you calculate R, you will find R is zero. Okay, Riemann tensor. 4 indices are alpha, beta, gamma. Okay? But remove this part and make it 2 dimensions. Okay? And do the same calculation. You'll find gamma is non-zero and the R is non-zero. Why? Because this describes the surface of a 2-dimensional sphere, which is not trivial. Okay? This is 2-dimensional calculation, not 3-dimensional as before. Okay? Anyway, these exercises are very important to give you the intuition about the geometry. Okay? And the calculation of gamma and R. Okay? Anyway, Maxwell's equation, back to special relativity. We want to formulate Maxwell's equation in a nice form, which is going to serve us very well when we discuss Einstein field equations. Okay? So we know two of the Maxwell's equations. I can write them on this form. I'm going to choose here C to be 1. Okay, so these two Maxwell's equation, of course I have another two, which is div B is 0 and curl E is minus partial B partial T. Okay, but let's discuss these two first. Okay, because these are very important. So if you try to make sense out of these equations, for example, using a more general potential, which is collecting the known potential, the scalar potential, and the vector potential in a 4 vector. Okay? So mu here is a 4 vector, like the 4 momentum, okay, the 4 space-time points. This is the electrostatic potential phi, and this is the vector potential of magnetism. So if you try to make sense of this and try to write down some equations for A, it won't work. You need to actually define a quantity which we call F mu nu, the field strength, which is partial mu A mu minus partial mu A mu. Okay? This field strength is actually the electric field and magnetic field component put in a tensor. Okay? So, or put in a matrix. You can actually have a matrix like this. You have 0 minus EX minus EY minus EZ, and the positive components here and the diagonal components of 0, and here you will get minus BZ, BY, and here you get minus BX. This is a skew symmetric. I didn't write down the rest here because it's known. You can get them from the right, because this is a skew symmetric tensor. That's to say, this is equal to minus F mu mu. Okay? So by putting or by defining this field strength, now you can write the whole two of these Maxwell's equation in this simple form. Partial mu F mu mu is equal to minus G mu. Okay? This is two Maxwell's equations. The other two, which are these ones, you can write them in this form. Partial mu F alpha beta is equal to 0. And this bracket means complete anti-symmetrization of mu, alpha, and beta. Okay? So these are, they have to be completely anti-symmetrized. Okay? So this equation will give you this one. This equation will give you these two. I mean, you can see directly how can you get this one from just putting nu equals 0. If you put nu equals 0, you have Fi 0, okay? Because 0, 0 is 0, right? And here you have partial I with mu, okay? And this will give you J0 component, which is rho. And you can see Fx0 and Fy0 and Fz0 are the component of the electric field. So this is indeed this equation in this case. And if you put mu to be I or J, you will get the other equation. Okay? Why this is important? Why we are going back to special relativity? It's very important because we are going to construct our general relativity field equation in the same form. we need an equation, okay, which has derivatives of the potential in the left-hand side and have sources in the right-hand side. Very similar to Poisson equation. Remember Poisson equation? Laplace square phi is equal to rho. You have some derivatives, second order derivatives over the potential, and this is giving you the sources that you have, okay? But the most important fact related to this form of Maxwell's equation is the following, is that Maxwell's equations in general are not consistent. Do you know that? If you wrote down these 4 equations that I'm writing, these are not consistent equations. There is an extra condition on them to be consistent. Do you know what it is? Exactly. Continuity equation. The 4 equations are not consistent unless the continuity equation is working, unless you have charge conservation. Okay? Yes.
Why do you write the field strength tensor in contravariant form?
It doesn't matter. You can write it whatever. I can put it here, and this will be, doesn't matter. Okay? Doesn't matter. It's just simpler for me to express it. Okay? So, but here this equation has very, very important fact that when you take a derivative, when you take an extra derivative here with nu and extra derivative here, let's have okay, you have nu mu here, okay, and can you tell me this tensor or this operator under exchange in mu nu, is it symmetric or anti-symmetric? Symmetric, because this is just a derivative. Okay? So this is symmetric. And what about this one? This is anti-symmetric. So a contraction between symmetric and anti-symmetric has to be 0. So this is automatically 0. So you get the continuity equation for free. Okay? You don't have to impose it. You get it here for free from this formulation. So I'm repeating this, or I'm actually presenting this in special relativity because we are going to follow the same lines, okay, when we discuss general relativity. We need some form like this. A derivative, some kind of operation here on the metric, and the right-hand side here, okay, should be in terms of some current or some physical sources. And when we take the derivative, when we take an extra derivative, a covariant derivative this time, on this left guy, okay, has to be 0, like this one, in order to have energy momentum conservation. Okay? So I'm repeating that, or I'm actually presenting this because we are going to follow the same lines. Now,
I can write the continuity equation from taking the divergence of the curve of the magnetic field. I think that's that the continuity equation is embedded inside the Maxwell equations. Is that true?
the continuity equation embedded inside Maxwell's equation?
Yes. If I took the divergence of the curve of the magnetic field, I would get 0.
Okay.
The curve of the magnetic field.
Okay.
The curve.
This is a curve, right?
I will took the divergence of the curve of the magnetic field. The other equation, the other.
Okay. Where is the other equation?
Ah,
this one? The divergence of the curve? Okay.
Yes. It will give 0.
Right.
And the divergence of the G
Right. ايه؟ لا لا هو divergence of curve.
Yes, yes.
ايوه هو كان مش قصده على الايكويشن دي، قصده على الايكويشن دي. اوكي؟ Okay, does this again, provided in the equation, the continuity equation is true, is providing that you actually are accounting for all the sources that you have in the problem. You understand what I'm saying? Because if you don't account for the electric sources that you have in the problem, you are not going to satisfy the continuity equation. Okay? So it is a consistency condition. Okay? That's to say, let's suppose that you have a region here, and you have your rho here, okay? And of course your current, your J is here, okay? If you account for all rho, okay, you will get a consistent continuity equation, okay? So in any case, it is known that, continuity equation is like an integral part of Maxwell's equation, okay? And in order to make the system consistent, you have to have a continuity equation, okay? That's to say, the charges do not disappear. So for example, if you have some physical process, let's imagine that we have some physical process which can make charge disappear. Then Maxwell's equation will not be consistent. Okay? Then this is the mean. Okay. Now let's go back to our track, which is trying to get the equations of general relativity. And let's go back to our classical gravity. So in our classical gravity, we have basically two equations. And the other equation is actually d square x by dt is equal to minus partial phi by partial. Let me work in, or just make it okay? So in order to study the physics of classical gravity, you have two equations. The first equation is the field equation, and the second equation is the equation of a test particle moving in this region. So if we assume that you know the gravitational or the mass density distribution in the region that you are studying, okay? If you know this, you can obtain phi, okay, by solving this equation. And when you obtain phi, you can plug it here and know how the trajectory of a small massive particle is going inside this region, okay? So in other words, you need these two equations, a field equation and a test particle equation, in order to describe gravity. And indeed, this is what we are going to generalize in general relativity. So we are going to have first a test particle equation, an equation which is telling me how a small particle is going to behave. And this small particle could be a time-like particle, let's say particle which has a mass, or particle which is massless, like a photon. Okay? How it behaves in the vicinity of gravity. And the other one is Einstein field equation. The generalization of Poisson equation is the Einstein field equation. And hopefully we are going to get it at the end of this lecture or next time. So let's try to get the generalization of the test particle equation, which we call geodesic equation. So of course there are so many ways of deriving geodesic equations, and I choose the simplest one, the most intuitive, and actually we get our results fast. So let's suppose that we have a curve. I'm talking about general space-time now. Okay? General space-time. But before we do that, let's suppose that we have a curve in flat space, in Cartesian coordinates, for example. This curve, I can always parameterize it with some parameter s. Let's say. How can I do that? Okay? Let's make a mark here and say that this s is 0 here, and s is 1 here, s is 2, and so on. Okay? So this is our parameterization of the curve. And this curve, I'm going to write it as x of s in the x direction, y of s in the y direction, and so on. This is my description of a curve. Okay? I'm embedding a curve, in other words, in 3 dimensions. Now, I can actually define a tangent vector on any point here of this curve, right? And this tangent vector, let me call it t, which is going to be dx by ds, which is dx by ds in the x direction, dy by ds in the y direction, and so on. Okay? This is going to give me the tangent at any point, s, right? Because I'm parameterizing in terms of s. Now, let's try to think together. If I want to actually, I'm talking till now Euclidean geometry, okay? The question is, if I want to actually define a straight line, or more generally, the shortest line between 2 points, how can I do that? What is the property of the shortest line, okay, between 2 points? This point, for example, and this point. And these arrows are the directions of the tangent vector at every point from point 1 to point 2. What is the property of this tangent vectors along the curve from 1 to 2?
In my direction.
It is the same vector, right? The tangent vector here is pointing to the same direction, at least pointing to the same direction, right? So if my tangent vector is pointing to the same direction, then this is a sign that I am along the shortest curve, or the curve of a shortest distance between 2 points, right? And what does this mean? This means actually that when I take ds with respect to s, do I have to get 0? No, because actually there could be some scaling here. That's to say, this is telling me that this tangent vector has the same direction, but it could have different magnitudes at different points, right? So this is why the derivative here should be some scale, which depends on s, times the vector again, okay? So this is a sign that this is a way of writing the change of the direction of the vector is the same, okay? So the direction of the vector is the same. Okay, now let's go to, now I think we agreed that the shortest, or the curve which has the shortest distance between 2 points is the curve which does not change its tangent vector direction. Okay? Now we are going to generalize this to a general space-time. And of course, this is a vector. Our t here is a vector. And remember our discussion about v, when we take the variation of a whole geometric entity and we expressed it in two pieces and we get the covariant derivative, right? We are going to do the same here. And by doing the same, we are going to get delta t alpha plus gamma alpha mu nu t mu delta x nu and this whole thing e alpha. Very much like what we did before. Okay? And now, when we take the derivative with respect to s, what we get is the following. So we get dt bar by ds is going to be dt alpha by ds plus gamma alpha mu nu t mu and dx nu by ds. Okay? And of course, this is equal to lambda s, okay, dx, you can call it alpha by ds, okay, or maybe we have it minus sign and we collect all this with e alpha to have a correct accounting for our indices. Okay? Now I can remove this because this is not correct and this is 0. Okay? So indeed, this is actually our geodesics equations. Okay? So our geodesics equation is telling us, let me write it in terms of, I'll remove every t capital. Remove every t capital and put actually the expression in terms of this, okay? So I'll remove t alpha and I'm going to put tx alpha by ds, or sorry, d, because this is a total derivative, okay? And in this case, I'm going to have d2 x alpha ds square plus gamma alpha mu nu dx alpha by ds dx okay equal lambda dx alpha by dx. This is the most general geodesic equation. Just a moment. This is the most general geodesic equation, but I can do one more simplification for it, that I can always reparameterize this curve with another s. Okay, let me call it s prime, in which lambda can be chosen to be 0. Okay, and in this case, I'm calling this s prime a name. It's called affine parameter. Okay, it's called affine parameter. So with respect to s as an affine parameter, this term here, I can set it to be 0. Okay, and this is the form that we all know. I mean, I don't know if you have seen it before or not, but this is geodesic equations for any test particle moving under the influence of some geometry in general relativity. Okay? It could be a null particle, it could be a time-like particle, Okay, because these are, remember, these are the only two physical cases that we have. Either it's a null or a timeline part. Yes.
Yeah, بس كان في مشكلة في النتيجة بس في دي سمول بعد الكونكشن
Yeah.
بس خلاص.
Because in my notes I did it as T, but I'm using also T for time, so it's better to be T capital. But anyway. Okay, any question about this?
هو دلوقتي احنا جبنا الفاريشن بتاعت
Right, the derivative with respect to S.
عملنا النكست
الايه؟
النكست بتاع على طول بقى
دي؟ دي انا عملنا هنا two steps. First express T, okay? Okay? And the second is we went to a fine parameter description. So we go to another parameter, it's called S prime, and this S prime automatically has lambda to be 0. So the right hand side now is 0. Okay? Good. More questions? More questions? Okay. So we obtained half of GR right now, and our target is to get the other half, the Einstein field equations, okay? And let's try to do part of this time, and maybe next time we'll do the other part. In fact, before we do that, it's very important to have a description for the matter sources, because we have ignored, or we didn't discuss matter sources so far. That's to say, I said here in our general relativity field equations, we are going to have on the right some sources. These sources are very similar to this J here in Maxwell's equation. And it's very important to understand how to construct them in order to have, because they need to be put in a tensor form. Okay? So this is what we are going to discuss here. How can we do that? So first, let's start with charge. Let's start with J as an electrostatic charge to know how we get them first, and then we will start with T mu nu. So first of all, I can define in special relativity, I can define a 4-vector u mu as dx mu by d tau. Here I'm going to actually describe a collection of particles like a fluid, okay? And these particles are time-like particles, okay? So this is why I can go to some frame in which these particles are at rest. Then my description for their motion is going to be through what we call the proper time tap. Okay? So this is why I have here tap. Okay? So this is our 4-vector, and we know from special relativity that this 4-vector, I can write it as gamma and the gamma mu r. Okay? I think if you have studied special relativity before, this is familiar for you. Now, we want to understand and express this continuity equation that we kept talking about. For a charge, okay, for an electric charge, of course, this continuity equation, we know what it means, okay? And now we want to actually understand more how rho actually and how J changes from the point of view of an observer at rest. Okay? Riding the particle, okay? And from a point of view of an observer which goes with the flow. So here I'm thinking about some fluid which consists of small particles, small massive particles, and I can take a cube like this, and this cube of course will contain few particles, and if I describe this cube now in the rest frame, right? Because this cube, if it has a volume V, okay, and a charge, an electric charge rho 0, okay, this is in the rest frame. How these two physical quantities changes from the point of view of an observer which goes with the flow. We call it co-moving observer. Okay? A co-moving observer, of course, will see this box here as going with some velocity mu I, right? So we need to apply whatever special relativity things on it. So let's start with the following. We have a rho 0, which is the density at rest. And the density at rest, I can write it in terms of the elementary charge of every charge we have times the number density, n, which I can express it as total n divided by the volume, right? So this is in the rest frame. But what if I want to calculate rho in the co-moving frame? In this case, rho is going to be gamma rho 0. But how can I get this? It is simple, because this box, if it's a cube and every side is L, the dimension along the direction of the movement is going to change to L prime, and this L prime is going to be the old L divided by gamma, the special relativity factor. This is going to change the volume like this. Volume is going to be not the volume, but volume divided by gamma, right? Because the volume is 3 L's. One of the L's is going like 1 over gamma, and then the volume is going like 1 over gamma, right? So this is how we explain this, okay? So first of all, rho is going to pick up a factor. That's one thing. And the other thing, J also is going to pick up a factor. Okay? So we'll have, because J is rho, let me deal with the components. The component of J is rho 0 times U. Now, if I go with no, let me just write it this way. Yeah. So Ji is going to be gamma rho 0 Ui. I think we can call it J0. Okay? So J also is going to pick up a factor of gamma. And now we are going to have a 4J, which is going to be rho 0 times U0, which is gamma, and rho 0 times gamma Ui. Okay? So this is like the definition, which is really rho 0 times U mu. Okay? So this is how we get J. Okay? And of course, we can use this to write partial rho by partial t plus divergence of j equals 0 as partial mu j mu equal to 0. Okay? So we know now how to describe a current and a charge density, okay, in terms of an observer which is actually going with the fluid. But what about the mass? What about the mass density? How this change? Does it change in the same way or different? So actually, the mass turned out to be a bit different. Why? Because look at the mass density. Let me call it G, just to distinguish it from the electric charge density. This is a gravitational mass density, okay? And what is rho zero? Again, it is the mass times what? Again, n divided by v, right? The number density. Now you have two factors of gamma here. From the point of view of the co-moving observer, as it looks as this box, we have two factors of gamma. First of all, you have a factor of gamma picked by the mass. Now I'm talking about rho from the point of view of the co-moving observer. So we have, and another gamma coming from V, okay? So I'm going to write it as N, okay? So, of course, this is gamma squared rho zero. So in other words, my new rho is going to be rho zero, u0, u0. These are the zero components of the four velocity, okay, which we have defined it here, right? The zero component of the four velocity. Just a moment, okay? Now, writing it like that, so now I'm familiar with the construction of the source on the right-hand side. Because of these two gammas, okay, that I have here, our generalized source, it has to be a tensor, second rank, because I have two indices here. Okay? So, when I go to a general setting, I have to have rho u mu u mu. Okay? And of course, I'm going to drop this rho zero from now on. So this is my source for mass density. Of course, this is a very simple situation in which I have zero pressure fluid. Okay? So the fluid I have discussed so far is very simple fluid. Fluid with zero pressure. But what happened when I generalize this to a fluid which has a pressure? In this case, I'm going to have T mu nu, which is rho plus P, U mu U nu, plus eta mu nu, some pressure. Okay? This is the most general perfect fluid sources in special relativity. Okay? And the way we go from special relativity to general relativity is simply by, this is the simplest way, by actually changing every eta, this is the Minkowski space, to a general metric. Okay? Which means that for GR, if if I have a perfect fluid case, this is going to be G. And this is what we are going to use in cosmology. Okay? So this is the source. Now I have the source. I think next time, what is the time right now? Yeah, I might just go very quickly over classical limit of general relativity, so we can so I have some derivatives here, as I said, some collection of derivatives. Let me just call it by partial, acting on some metric, and on the right hand side I have T mu nu as a tensor, and here I have some second rank tensor. I have some derivatives here, a collection of derivatives, okay? Or maybe it's better to just call it x mu nu, which depends on the metric and its derivatives. Okay? So till now this is what I have, and I know how to construct T mu nu. Now we are after the left hand side. How can we think of it? The way we think of it is the classical limit. How we get from this theory to Newtonian physics. Okay? So in order to construct a theory, any theory, it's very important that this theory is a generalization of something that you know, first. Second, you need to know exactly what to do in order to go from this general theory to this less general known, well-established theory. Okay? So this is what we are going to do. Again, as we said, our classical mechanics telling us that, and I'm going to write everything here with full details because we are driving the field equation. And the second equation is that okay, so these are the two equations, and in order to get them out of this one, I have to have certain assumptions. So what are the assumptions? First of all, I should go to non-relativistic velocities, right? And this I can express as the dxi by d tau, the velocity, is less than dx0 by d tau. So this is actually, in special relativity even, is going to be gamma. Okay? And this is saying that really gamma is close to 1. Right? So if V is much, much smaller than C, gamma is going to be 1. Okay? So we are saying that dx by dt by d tau has to be much less than 1. Okay? And dx0 by d tau is going to be 1. This is the limit we are talking about. The other limit is that we go to a static description of gravity. Okay? We know that Newtonian gravity does not, okay, describe very well time-varying gravitational field. So d g mu nu by dx nu by dx0 actually, which is time, is 0. Okay? So we go to a static limit. In order to get this, okay? In order to get classical gravity, we need these two. And the third one, which is very important, that our metric is going to decompose into the Minkowski metric plus some small correction. This is small. And small meanings if you find two h's multiplied together, this is really small. So you would ignore it. So just keep whatever order 1 in h. Okay? Now, what we are going to do here is to go back to our geodesic equations and try to see what we get in this limit. So in this limit, as you can see, what is left, okay, because the summation here over temporal and spatial components. So the spatial components are very, very small. Okay? So this means we are left here with d square x mu d tau square plus gamma mu 0, 0. dx 0 by d tau is 1, and this is 1, so this is 0. This is the equation we have. This is the approximation from here. Okay? Now, if we take the 0 component, okay, let's take I here. So this is, if we take the 0 component, we get 0 also. Okay? And this is because of the gamma. Gamma, let's say gamma mu 0, 0 is half g mu alpha partial g 0 alpha by partial x 0 plus partial g 0 alpha partial x 0 minus partial g 0, 0 by partial x alpha. Okay? You will find that because of static description, this is 0, this is 0, and we are left with this. Okay? So we have here minus half g mu I partial g 0, 0 by partial x I. Okay? So gamma is proportional to mu I, and I is a spatial coordinate. So mu has, of course, temporal and spatial. With temporal, this is 0. Okay? So this means for the temporal part, I have x0 by d tau squared. This is 0. A second derivative with respect to something is 0. It means what? It means x0 is linear in tau, right? So really, x0 is tau. Okay? So we are going to take here x0 to be tau, more or less. Okay? And now if we go ahead, you can see actually that the g00 component, okay? Because the only surviving here is mu equals to I in order to have I, and this is to be 1. Okay? So if we put everything here, now we get the following. We get dxi by d tau square. Okay? This is equal to, after we ignore some terms, a very similar thing to what we have here, right? So this is actually relating phi, the Newtonian potential, to h00 and g00, right? So this is really saying that phi is nothing but minus half g00 plus 1, okay? Now let's plot this here. Of course, it will be trivial, but let's plot it here and put everything that we know. So if we do that, we'll get this equation: nabla square, okay, G00 is equal to minus 8 pi G Newton T00. And by generalizing this, okay, this is of course part of a tensor, and this tensor should be covariant derivative. This is a spatial derivative, okay? Maybe you just make it bar just to distinguish it. But this is covariant derivative. This is T alpha beta. So this is the equation we might guess from this discussion. Okay? So this is our proposed general relativity equation, which is of course doesn't look like Einstein field equation because it is wrong. This equation is wrong. Why is wrong? Because there is a fact that we are dealing with. I mean, our construction, our geometric construction here is what we call Riemannian geometry. And in Riemannian geometry, the covariant derivative acting on the metric is zero, which means the left-hand side is trivial. So the left-hand side is zero, but the right-hand side is not zero. So obviously, this is a wrong equation, right? So we'll go back to our general construction that we need something, okay? We need something like this. We need some second rank tensor, okay? When I take a covariant derivative for it, should give me zero identically. Very similar to what happened here. Here I got it identically. Okay? So this is what we are going to discuss next time. Okay? How can we construct a general second rank tensor? Now it has to be in terms of curvature. Okay? Not to be trivial. Okay? And see you next time. All right. Any question before we go? Yes. Yes.
تمام. هو in what sense احنا اصلا define السكيلرز انها invariant number transformations. يعني هي المفروض الناس نفسها لما تتغير من اول سيستم تاني.
مين اللي قال ان الماس دي سكيل؟
عليها فيكتور؟
هي كومبوننت. الفور مومنتوم الفيرست كومبوننت فيه ماس، هي التمبورال كومبوننت بتاعت الفور فيكتور. فهي بارت اوف ا فيكتور، فالترانسفورم از ا فيكتور. ودي الترانسفورميشن بروبرتي بتاعتها ان ام 0 بتاخد جاما قصادها. تمام؟ It's very important because this is very deceiving. Okay? انت you need to know the transformation بتاعت everything in terms of Lorentz. And from Lorentz you would know if it's a part of a vector or a tensor or it's a scalar. Okay? Any other question? All right, so let's have our break and come back. We have a break now, right? لا خالص. اسأل واسأل أكتر. ماشي؟ خالص. خلي بالك إن ممكن يبقى في ناس تانية موجودة وتتكسف تسأل فهو الأسئلة دايما حاجة كويسة. تمام؟